I'm going to use the Taylor expansion with Cauchy remainder to approximate the value of fifth root of 2. So first of all, let me explain why does the Cauchy remainder look like this. So first of all, according to the original definition, the Cauchy, because first of all, here I have the first n plus 1 terms of the Taylor expansion, right? So the Cauchy remainder, Rn of x originally looks like the, first of all, n factorial. Then we have the n plus 1th order of derivative at some point, Cauchy. Right, let's say we expand over the interval 0 to x. Like I said, 0 over x, this closed interval, restrict x in between -1 and 1. So meaning the Cauchy is some point in between this and that. Right? Maybe Cauchy is somewhere here. Right? So bigger than 0, less than x. Right now, treating x as a fixed point. Now then we multiply by x minus Cauchy to the power of n, then minus x minus 0 to x minus 0. So x minus 0. Right? So then we can just replace Cauchy with theta times x, right? Cauchy with theta times x. The reason is because if we restrict theta in between 0 and 1, if we multiply by x, we get theta times x is right now, because I'm treating x, if x is bigger than 0, then we have x and 0. Right? So theta x is really between 0 and x, right? So Cauchy really can be written as theta x. So n factorial, the n plus 1th order derivative at theta x, theta between 0 and 1, multiplied by x times, again, theta x to the power of n multiplied by x. So again, so what's the n plus 1th order derivative? Right. First of all, the first order derivative is lambda times 1 plus x to the power of lambda minus 1. Right. Then we continue to take down the power, just continuously. Then we should have lambda times lambda minus 1 all the way down to just, because if it's second order derivative, then we have two terms, right? This term and that term. If we have take n plus 1th order derivative, we should expect to have n plus 1 different terms, right? 1, 2, 3. So I should have lambda minus n plus 1 minus lambda minus n, because lambda minus n minus lambda, I have, sorry, lambda minus this term, I have n, I should have n plus 1. Because lambda minus this is 1, 1 plus 1 is 2, two terms. So this is exactly what I should stop, where I should stop. So again, so then I have 1 plus x to the power of lambda minus n minus 1, right? Then I should replace, so x minus theta x and x. Like I said, then I should replace x with, because generally speaking, that's any point x, right? Then I should replace x with theta x, right, where x was. So theta x. Now this time I have this expression, right? So lambda times all the way down to lambda minus 1, right? N factorial, n factorial. 1 plus theta x, 1 plus theta x to the power, same power, right? Then I have x minus theta x to the power of n times x, treating x as a fixed point. So this is my Cauchy remainder. So then I have to estimate the absolute value of Cauchy remainder, right? And then of course, first of all, I have this and that. So minus power, minus n and n, maybe I should put this down on the denominator. So that is equal to n factorial lambda times lambda minus 1 all the way down to lambda minus n. And if I put this down on the denominator, I have 1 plus theta x. And I should extract x out. Right? X out, and x to the power of n times this x. Then remember, in the end, I should times x to the power of n plus 1. Right? So I'm left with just 1 minus theta quantity to the power of n. Right? So 1 minus theta quantity to the power of n, altogether to the power of n. So I'm left with just 1 plus theta x, because minus n power has been already used. I still have power of lambda minus 1. Right? Everything else is good. So I just multiply by 1 plus theta x to the power of lambda minus 1. Right? Because this x to the power n extracted, distributed to this x. Right? And this is what I have, Cauchy remainder. So then I'm going to make the claim. I'm going to make the claim that this base 1 minus theta over 1 plus theta x must be greater than 0 and less than 1, so that I can get rid of the theta. And later I'm going to estimate this term to get rid of this theta. All right, so hopefully in the end I can just reach some estimation without theta at all. Because that's the most difficult part. Because we don't know where this Cauchy is. In other words, we don't know where this theta is. So first of all, so 1 minus theta over 1 plus theta x has to be bigger than 0 and less than 1. The reason is because all I have to do is to show that, because first of all, theta is between 0 and 1, right? So 1 minus theta must be positive, right? Has to be positive. Then of course, 1 plus theta x, because like I said, x is in between negative 1 and 1. So x is in between negative 1 and 1. Multiply by theta. Theta is positive, so we're fine. Less than theta, bigger than minus theta, right? If we plus 1 on both sides, right? Plus 1 on both sides, less than 1 plus theta, bigger than 1 minus theta, right? So really, I've reached this conclusion that 1 plus theta must be bigger than the top, right? 1 minus theta. And 1 minus theta, like I said, has to be positive. Right? So if we just divide this thing over down here, right, we must have 1 plus theta. Everything is positive, so the inequality remains, right? So it must be less than 1, still bigger than 0. Right? So my claim is correct. So now as I estimate the absolute value, right, absolute value, then I can just get rid of this part, right? Because this is already positive, so maximum can only be 1. So if I replace it with 1, then it's become bigger, right? So So therefore, I can draw the conclusion, Cauchy remainder, absolute value, not only bigger than 0, but less than or equal to the, first of all, n factorial, absolute value of lambda times lambda minus 1, all the way down to lambda minus n absolute value. Also, times 1 and times this, right? 1 plus theta x to the power of lambda minus 1 times x to the n plus 1, right? So my job now is to further estimate this part, right? I want to get rid of all the thetas, right? Because that is the tricky part. So now 1 plus, because in the end I should have, remember, I should have absolute value, right? Absolute value. So absolute value, right? So the absolute value of 1 plus theta x, right, I want to further estimate this. So it seems like I can use triangle inequality, right? First of all, it's smaller than 1 plus theta x absolute value, right? So theta, like I said, maximum, it can be just 1. So replace it with 1. No bigger than 1 plus x absolute value, right? So bigger than or equal to, again, triangle inequality. So 1 minus the absolute value of theta x. Right? So again, if I replace theta with 1, right? So theta absolute value times x absolute value, right? So the x absolute value is already positive. So times a factor maximum is just 1. So maximum, I can make this absolute value reach x absolute value, right? That's the maximum point. So since I have a minus sign in front, so in the end, the minimum possible value of this whole left-hand side can only reach 1 minus absolute value of x, right? That's the minimum value. So in the end, my conclusion is that absolute value of 1 plus theta x is no larger than 1 plus absolute value of x, and no smaller than 1 minus x absolute value. Right? So now my conclusion is that I can analyze the Cauchy remainder further. Right? More precise estimation is no larger than n factorial, absolute value of lambda times lambda minus 1, all the way down to lambda minus n multiplied by, so like I said, of course, then we have to analyze if the power lambda minus 1, is it, if the power is positive, then of course it's an increasing function. Then we can just maintain the direction. Otherwise, if the power is negative, maybe we should change the direction. So like I said, if the power lambda minus 1, if it's positive, then we maintain the direction. Right? So if lambda minus 1 is positive, in other words, when lambda is bigger than 1, then we have the Cauchy remainder absolute value is no larger than, like I said, maintain the direction. So we raise to the power of lambda minus 1, still less than or equal to this quantity raised to the same power, right? And we copy down the rest. So n factorial absolute value lambda times lambda minus 1, all the way down to lambda minus n multiplied by 1 plus absolute value of x quantity to the power of lambda minus 1, same power, multiplied by absolute value of x to the power n plus 1, right? So I'm done with this part, right? This is verified. All right, when lambda is bigger than 0, or bigger than 1, we're fine, right? So if lambda minus 1 power is negative, in other words, when lambda is less than 1, then we have the absolute value of the Cauchy remainder is no larger than the still copy down the first part, absolute value, lambda times lambda minus 1, all the way down to lambda minus n multiplied by, like I said, since now the power is negative, right, then we just change the direction of the inequality, right, since it's now a decreasing function. So, in other words, originally this is bigger than that. Now we say this must be less than raised to the same power, right? Same power, less than this. So, again, copy down. So 1 minus absolute value of x quantity to the power of just lambda minus 1, negative power this time. Still copy down the remaining. X absolute value n plus 1. Right, so I'm done with this. Now we can roughly just estimate the fifth root of 2. So first of all, we're going to find a number that's close enough to 2 when we raise to the power of 5. For example, if we choose 6 over 5, that is 1.2. So it turns out that if we raise to the power of 5, then it's close enough to 2. It turns out to be very close to 2, a little bit bigger than 2. But now we can just simply just rewrite 2 into, so 6 over 5 to the power of 5. Right? Then we minus the same thing. And we plus 2. Right? Still the same thing. So again, it is equal to, we can just, first of all, copy this down. Factor out this thing. Right? Factor it out. Maybe I can just write minus 2 altogether into the bracket. Or I can factor out this thing. Then I can have just 1 minus the 2 times the reciprocal of this thing. Then I have 6 to the power of 5. Then 5 to the power of 5. 5 to the power of 5. Multiplied by this. Then I can just five minus the same thing. Again, common denominator. This. So it turns out to be turns out to be 1526. Yes, 1526. So again, so I can factor out this thing. Right, factor this out. I still have 1 minus this fraction. So again, this fraction is actually also very small, smaller than 0.2. I'll discuss that later. So now I can first of all take the fifth root on both sides, right? So the fifth root of 2 is now equal to the fifth root of this whole thing, right? So this 5 is cancelled out. 6 over 5 multiplied by the 1 minus the fraction. Actually, maybe just let's denote the positive fraction as some positive number delta. So delta. So minus delta to the power of 1/5. Again, so this is actually the, so when lambda is equal to 1/5, we have Taylor expansion. So that is equal to, copy down this thing we have. First of all, first term is 1, right? Lambda times x. So lambda is 1/5. X is this thing. So minus, I have minus 1/5 times delta. Right, delta. So this delta. That's plus half of lambda times, so then times x to the power of 2, right? So minus lambda to the power of 2. So plus. Lambda minus 1. Lambda minus 1, 1/5 minus 1. That's, I think it's negative 4/5. I have to multiply by x squared. X squared is the input, so no more negative in here. So delta squared, right? But negative. So this guy will still become minus, right? Minus gone, right? Minus distributed here. So I have this multiplication. Right, so still minus some positive number. Then of course next is what? 3 factorial. Just lambda times lambda minus 1 times further this guy minus 1. That is negative, just I think it's 9/5. I keep minus 1, minus 1, minus 1. So times x to the power of 3. So this guy to the power, still negative, right? Still I have negative delta to the power of 3. Right? So this negative, 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 positive, still negative. So still change this into negative. So everything else is just positive. Right? So this time we multiply. Right? Then maybe I just plus a Cauchy remainder. Right? R3 of x. Right? X is minus delta. Right? So this time, like I said, this time. So in the end, this turns out to be okay. So this is approximately 2.48832. So this very close to 2. So now this result, so okay. This turns out to be, including the multiplication, including multiplied by this fraction. In the end, overall it's 1.1487686. Now that's according to this formula. And then we use the estimation. That's the estimation of the Cauchy remainder. Absolute value. So this turns out to be, again, so this is, we use this part, because lambda this time is less than 1. So this estimation, right? So 3 factorial, lambda time, so absolute value, right? So lambda times lambda minus 1, lambda minus 2. That is, I think it's this thing, right? So times 4 over 5 times 9 over 5, right? Or everything is positive. Multiply by 1 minus x absolute value. What's the x? This absolute value, right? So minus lambda, minus delta, right? Positive. So power of lambda minus 1, 1/5. So minus 4 over 5. Multiplied by x absolute, delta absolute value to the power of lambda n plus 1, 3 plus 1, that's 4. That's power of 4. So this Cauchy remainder absolute value is no larger than this. Right? So delta is this fraction. Right? So it turns out that turns out this is no larger than 0.0002492. Right? So which means the estimated value of the fifth root of 2 with the actual value of the fifth root of 2, their difference is no larger than this value. Already very precise, right? So according to the calculator, the actual value of the fifth root of 2 is just 1.1486983. So already very precise. So we have 1. So the first 3 digits after the decimal are exactly the same, except we have 7 compared with 6, right? So the margin of error is already below the just third digits after the decimal.